All right, last time we took a look at section 2.1, Numeration Systems. And as we were taking a look, I believe we had gotten to the point of doing Roman numerals, and you guys were given a very brief assignment. Did anyone look at the clock tower? That's a nod. What did you discover about the clock tower? Brianna?
4 eyes.
4 eyes. And you will find that on clocks quite often, actually. I had actually a mom at my church was talking about her son looking at a watch and saying there's something wrong. And it was the same thing. So if you look at clocks often, even if they have Roman numerals on the clocks, it will have the number 4 written as 4 eyes, which is not correct, right? How should it be written? IV. Very good. All right, we're going to take a look, starting back with Roman numerals, at the other feature about Roman numerals that we didn't get to last time. This one right here. So let me just remind us where we were before on the Roman numerals. We had I and V, X. Those are the ones that you remember for sure. And then after that, we have L is 50, C is 100, D is 500, and N is 1,000.
I'm sorry, that just came on for no reason.
Okay. All right, and so we talked about how to sort of abbreviate some of our writings without having to write, for instance, a lot of digits out. And they had a subtractive feature. We talked about the subtractive feature only really applying to the numbers that we would call 4 or 9 in a number digit expansion. And then we have this one other feature about their system that allows us a way to write numbers bigger than 1,000. So in order to write a number that's larger than 1,000, we have a multiplicative property that has a bar placed over it. So for instance, if we want to write something that has the number 9,000, you want to think about that comma with whatever's after that as being separate from the 9 that's before. So just for a moment, if you will, how would you write the number 9? IX, right? So if I write the number 9, I write it as IX. The way that I represent then that that's the number 9,000 is that I write a single bar on top of the IX. And that's all there's to it. Single bar. If you wanted the number to be in millions, you would write 2 bars, just horizontally stacked. So if you had the number 9 million, you'd write that same IX, but then you put 2 bars. They should be the same length. Sorry, that looks funny. But it's the number 9 million. Okay? That's how you do it. Now, anything else that comes after that, if there had been numbers here, like let's say instead of having 3 zeros, we had 423, well, then we'd just keep going. We'd have the 9,000 right here written as the IX with a line on the top, and then we'd write out what would look like for the number 423. Okay, so none of that affects what happens next. The bar just applies to what happens before the thousands place. So let's take a look at an example where we're looking at numbers before and after. All right, so we have the number MCMX. There aren't any bars in this particular one, just MCMX. Now, on most of them, we haven't really focused on what that number is, but we could, and with Roman numerals, it's often helpful to think about simply because we do still see them used today. So what does the M represent? That's the number that's 1,000. What is C? 100. What is M? 1,000. And then X is 10. So the first thing that you should notice is that looks weird because I went 1,000, then I went 100, and then I went 1,000. Why? What's happening there when I have that 100 in the middle of something larger than 1,000? Very good, Audrey. There's a subtraction feature going on right here because I have the number 100 smaller than the number 1,000 and it's coming beforehand. So those two are sort of grouped together. And what is the number that's 100 coming before the 1,000? 900, right? Yeah. So this 1,000 right here, this is 1,000. And this is 900. Let me write it as addition. And then I'll write it all together. And there's a 900. And then what's at the end? 10. So what is this actual number in our system called? 1,910 or 1910. Could be a year even, right? Especially because we were talking about years. Sometimes we'll hear on buildings in the older parts of the country. All right, so I'm not so concerned that you can do this all the time, except that it's something you should be able to decipher if you come across it. But let's take a look at this idea of going before and afterwards. So we actually did part C. I guess we're going all out of order today. All right, there's the 1910. I did it already. Let's go backwards and go to the 2 pieces I skipped. All right, part A, it says, what Roman numeral comes before this value? Well, the issue is actually all about the last digit, 10, right? Just like we were looking at the other numeration systems. It's all about what happens at the end of the number, the smallest digits of the number. So the number that comes before 10 is the number 9. So the values at the beginning don't change. So I still have the M, the C, and the M. But instead of the X for 10, how do I represent the number for 9? IX. That's the number 4. And then what do I do to get the number after? XI. So the MCM stays the same, but then I wanted to have the number that represented 9. Now I want the number that represents 11, and that's X and then I. Same symbols in a different order, and all of a sudden it really does matter the order on this, doesn't it? It really does for Roman numerals. The order is very important. All right, and we already said that this is a digit 1910. Let me do another one. This one has us going the other direction. I'm going to take the number 1,492,019. And what we want to do is we want to figure out what in the world is the Roman numeral that's equivalent. Can you see a paper? Okay. So when I'm looking at this is a very large value, right? I mean, comparatively to the 1910 we just worked with. In particular, it's larger than the number 1,000. So we probably got some multiplication bars going on. Does that make sense? So what I'd like to do is I'd like for you to consider this in terms of those commas. They break this thing apart, right? The number that's at the very beginning is the number 1. How do I write the number 1 in Roman numerals? I write it as an I. But this number 1 is in the millions place. So how do I represent that in Roman numerals? 2 bars on top of it. Sorry, it should not look like a T. Let me try that one more time. There we go. So there's that I with the 2 bars on top. So we've done the number that's before the first green vertical line that I drew. Now we're going to do the number that's between. I need to represent the number 492. So we go with it one at a time. How do I get 400? CD. Okay, so I'm using a subtraction feature. Anytime you see the numbers 4 or 9, subtraction features are going to happen, right? And this is the number 4 for 400. So you might think 400, well, I can just write 4 C's, but you never write a value more than 3 times. That's why we would not write 4 C's. So we have to use a subtractive feature, C and then D, because C's worth 100, D's worth 500. So far, so good? Okay, 92. I've got the 90. Now, how do I write the number 90? XC, very good. Again, it's a subtractive feature, right? I've got a 9, and I would not write 90 with the 50 plus 4 tens, because that would mean 4 digits that matched. So I'm going to use 90 as the number 100, that's the C, minus the number 10, which is X, and so it comes in front. So this is represented as 10 minus, or 100 minus the 10, which is the 90, so the 10 comes in front. How do I get the number 2 right here? 2 I's, you bet. All right, so what we've written down right now is 492. How do I represent that this is supposed to be 492,000? 1 bar on the top of that piece right there. Almost done. I have the number 19. How do I get the number 19? Well, start with the number 1 that's in the tens place. How do I get the 1 that's in the tens place? X. This number right here is X. And then how do I get the 9? Close. IX. There you go. 9 is IX. And there's no bars on top of that because that's actually the number 19 that I'm trying to represent. Yes, Brenda? That first X came from this number 1 right here. That's 110. Yeah. Think about it in terms of money. I think it helps a little bit. If I were doing $19, I would have a $10 bill. So I've got one $10 bill. And then the 9, well, in our system, we would have 5 and 4 ones. But we don't do 4 ones in our system. You don't repeat a number 4 times. So we've got to represent that subtraction feature. Does this make sense? Okay. All right, something else in this section. So we're going to move a little bit beyond now the whole idea that we were looking at with the different numeration systems, and we're going to talk a little bit about place value. Place value manipulatives, and I did mean to bring these this time, I'll bring them next time, can be done with base 10 blocks. Have you seen base 10 blocks before? Anybody seen those before? Okay, I will bring them next time so you can see them because I have base 10 blocks back in my office. Base 10 blocks have blocks that represent our base 10 value system. So they first have one of them that's called a unit, so it looks like a small square. Okay? And then they have a long, and a long actually looks like 10 of those units put together. And I'm not going to draw all the 10 units in there, but there are 10 of these side by side. Okay, so this one has a value of 1. This one has a value of 10, because there's 10 of the small blocks stuck together. A flat actually looks like 10 of the long bars stuck together. Okay? And so if you have 10 of the longs stuck together, and a long is 10 of the units, there's 100 here, correct. This is the number 100. There's 100 little small blocks there. If you've taken math 2, this looks like the decimal grid that we did before. Remember that? There's 100 of those little blocks stuck together. And then, or the little units stuck together. And then we have what's called a block, and sometimes it's called cube, depending on what resources you're looking at. And what it does is it three-dimensionalizes this picture. So I'm going to have to draw it just a little bit smaller just to give myself enough place to draw the picture in. But imagine if you put 10 of these flats together and turn it into a cube shape, like an ice cube. Okay? What do you think this one's worth? How many little bitty unit blocks are there? There's 1,000. What this does is it gives a visual representation for our base 10 system. And I apologize if I don't have my blocks, but I will bring them next time so you can actually see what they look like. These are often used in elementary school when you're talking about addition and subtraction. This makes it very clear why, for instance, I can add 10 and 3 together and get 30. Because they're in the same size block. I can't talk about them that way. I work with my son with money, and he does this with coins, for instance, right? What do kids do with coins? They just count coins like they're all the same. But you and I both know that a quarter's worth more than a penny, right? Because they're not the same kind of coin. The same thing happens when we're working with these types of manipulatives. They're not the same kind of blocks, and we can't just count them as though they actually are worth the same amount. There are other number systems that you can do these blocks with as well. You can do these blocks with base 3 blocks, base 10 blocks, or base 7 blocks, base 12 blocks. They work all the same way. But I want to talk to you a little bit about these systems and show you how they work in these systems. And I actually have base 3 blocks as well in my office, and I'll show you those when I bring them next time. So if you take a look back at this base 10 blocks right here, I had told you that this unit was worth 1, right? It's one single block. And a long is worth 10 because we're working in base 10. When you're working in another base, those longs are worth different amounts. So when I bring you my blocks, you'll see that a long in base 3 is worth 3 blocks because it's base 3. And a flat is a 3 by 3 square, which would have the value of 9. 3 by 3, right? 3 wide, 3 tall. It's 9 in area. And you could do the same thing with the third dimension, or like 3-dimensional shape down here. You'd add another third dimension and you get 3 times 3 times 3, which is 27. So we're going to take a look at that idea and talk about other number systems. So let me first talk to you in general about other number systems. Whenever we get to this point, I think students sometimes a little bit mentally check out because they're thinking, I'm not teaching other number systems when I get to teach 3rd grade or whatever it is grade. And while that is true, there's a couple of things I want you to be aware of. Number one, you do use some other number systems all the time. You've got one right on the wall over there. That clock does not use base 10 number system, right? It doesn't. You guys start over counting after you get past 60 minutes, right? We don't have 100 minutes on a clock face. And we can talk about 100 minutes and it makes sense, but we talk about it usually in terms of the number of hours and the number of minutes after we get past 60. You use base 60 frequently when you look at minutes and seconds of the clock. You also use base 12 when you look at the clock. or 24 if you just so happen to think you want to use military time, right? You start over counting. We don't talk about the hour as the 25th hour of the day. That doesn't even make sense to us. We don't keep going. You also use different number systems when you work with inches and feet, right? We don't talk about something usually being 25 inches. We talk about it being 1 foot and 12 inches, or 2 feet and 1 inch. Get the right numbers in there for you. Give an example for it. We talk about things in terms of feet and inches. We use a base 12 type of a system. Does anybody else know do you know of any other basis systems that you've heard of being used, or maybe not you directly have used them, but there's a couple of others that are used? If you've done anything with geometry or trigonometry, on a unit circle, like a circle, you talk about 360 degrees. That's another example. If you've done minutes and seconds, sorry. So you can still go. Yeah, it's counting. Okay. If you do minutes and seconds in terms of degrees, that's actually done with the base 60 numbering system as well. Another one is, if you guys ever heard somebody talk about binary, you've heard that phrase before. I mean, I'm not asking you to know what it is, but if you've heard it before. Binary is computer programming, how computers are done. It's used binary as base 2. So computers are programmed in one of two systems typically. Base 2, which is binary, or base 16, which is hexadecimal. Other base systems are used for computer programming, another real common one. We're going to use them just in general, and part of the reason why you're encountering them here is because I want you to get beyond the idea that addition and subtraction is easy because you've been doing it for like 15, 20 years. You've been doing addition and subtraction for a long time. So it's really hard to imagine sometimes, why in the world would this be difficult? Are you guys following me? Because I'll tell you what, it's beyond my son. He's not encountered it yet, and he just looks at me with this glazed over look on his face. He has no idea why in the world the quarter and the penny, when I count them, can't be counted the same. It just doesn't make any sense to him. Okay? But you guys know, because you've worked with those pieces of equipment now for a long time. So we're going to work in other systems to put you back in that place where you actually have to think through why things work. That's part of it. So let's take a look at 3 other number systems, and we could do this with anything. I'm just choosing base 3, 7, and 12 to think about. All right, so in our base number system, how many digits do we have? How many single digits do we have? I think we've already talked about this once. How many? More. We have 10. Audrey, which one's she forgetting? 0. We actually start with 0. So when we're doing our base number system, we have unit single digits that go from 0 to 9. We don't actually have a 10 in base 10. Right? Yeah. We actually mentioned that, I think, last time, but it didn't. Okay, I'm not imagining that I'm going to a different class. Okay. So we always start with 0. We will have a 0 no matter what base we're in. Okay? Now in base 10, we go from 0 up to 9. We have 10 digits because it's base 10. So what would my digits be in base 3? First 1, and then 2. How many digits do we have in base 3? 3 digits. That's not by accident. That really is the way it's going to work. Okay? Base 10, we have 10 digits. We don't have a 10 in base 10 that's a single digit. We don't have a 3 at all in base 3. We have 3 digits. They're the numbers 0, 1, and 2. Base 7, what do you think the digits would be? 1 through 6, after the 0, right? Yeah. I'm going to talk about what happens next after we run out of digits, but I just wrote 7. That didn't really happen. No, of course not. All right, base 12, we run into a problem. Any idea what problem I'm going to run into? I'm going to have double digits if I only use the digits we actually have in base 10. I'm supposed to have how many digits? I'm supposed to have 12, right? Because I'm in base 12. So the first few of them, I can get 10 of them that match our system. run out of digits. And that's the reality, right? I had run out of digits. But I'm supposed to have 2 more. But if I change it to a 2-digit number, it's not a single digit anymore, which is sort of counterproductive, right? I'm supposed to be using that many digits. So what your book has you doing is it has you using T for 10 and E for 11, and you might just note to yourself somewhere else on the page, this is not part of base 12. But if we were working in a bigger base, they're using W for 12. If you've done contemporary math, this is not what your contemporary math book did. Do you remember what it did? Do you remember? I like what it does a lot better. It uses the letters of the alphabetic order. So it does A for 10, E for 11, C for 12, and so forth. I get why we're using T and E. I get it, T for 10, E for 11, but the problem is once you run into 12, you can't use T again. And so we've got to come up with something else. But this is what your book uses, so we're going to go with it. In base 10, what do you do when you run out of digits? What comes after 9? In digits. A 1 and a 0, right? In our base 10 system, when we run out of digits, that is, if I were to write out the digits past 9, I would need 2 digits. And the 2 digits would be the numbers 1 and then 0. The same thing happens in every other number system as well. When I run out of digits, I have to go to a 2-digit number. And the 2-digit number is the smallest value that we can do with 2 digits. And it's always 1, 0. Now, let's go one at a time here. In base 3, what would come after 1, 0? 1, 1. And then 1, 2. I mean, I've got all the digits 0, 1, 2, 3, or 0, 1, and 2, right? So I can have a 1, 0, a 1, 1, and 1, 2. Can I have a 1, 3? No, because there are no 3s. So I've run out of digits again. So what happens once we get to 1, 9 and we've run out of digits in our base system? What do? We make the last digit a 0 and we increase the first one, don't we? 1, 9 is that's as big as I can do 1 with a digit after it, 1, 9. So when I run out of digit 9, I have to turn it back into a 0. And I increase the number that came before. So I get 2, 0. And we can keep doing this. I would get 2, 0, 2, 1, 2, 2, and then would I get 3? Actually wouldn't, right? What's the problem when I get to 2, 2? I've used all the digits, haven't I? That's all of the 2-digit numbers. That's the biggest 2-digit number there is. So what would I have to do? Go to 3 digits. So after 2, 2 would be the number 1, 0, 0. And we would keep going up from there. Let's think through this the same way. We won't go as far, but with base 7. What would I do in base 7? What would come after 1, 0? 1, 1. And I would keep going until I got to what?
What's the 6?
1, 6. And what would come after 1, 6? 2, 0. Now what's the biggest 2-digit number in base 7? 6, 6. You guys are doing great. That's exactly right. Once I got to 6, 6, I would be out of digits. And I would then move on to digit 1, 0, or the numeral 1, 0, 0. Base 12. Base 12 is weird, right? Because base 12, I have these extra letters at the end. So I actually get all the same digits I get normally in base 10. So I would go from 1, 0 all the way up to 1, 9. What would come after 1, 9? Not yet.
The 1 T.
1 T. And then 1 E. And then I would run out of digits and I'd have to go into 2, 0. And then I could go all the way up to 2, 9, 2 T, 2 E, 3, 0. What is the largest base 12 2-digit number? It's EE. Very good. Okay? Your feeling a little bit uncomfortable, it's okay, I promise. It's weird, right? This isn't what you're used to thinking and feeling about, right? This is not how it works in base 10. All right, so we're going to do the same thing we were doing in the other number systems. We're going to try and find the numeral before and after, preceding and succeeding each value. So what would come before? This is base 5. I know it's awfully tiny here. This says 1, 4, base 5. What would come before 1, 4? 1, 3. The preceding number would be 1, 3. And you need to write down next to it that it's a subscript 5. That's what identifies which base system you're in. And please do write the word, because if you write a number, it's probably going to start to look like the number 1, 3, 5 instead of 1, 3, base 5. So that's why you're going to use the word here. What about afterward? What comes after this? What is it? It's 2, 0. Why isn't it 1, 5? Because it's base 5, and we do not have any digit 5 in base 5, right? Yeah, that's right. All right, how about 2, 0, 0? Sorry, 2. T, 0, 0. This is base 12. Let me suggest we do the easy one first. Can you tell which one's the easy one? Preceding or succeeding? Succeeding is the easy one. What is the succeeding term? T01, absolutely. And again, base 12. Why is the preceding term the more difficult one? Because it has those zeros at the end, right? So what's probably going to be easiest for you is to pause for a moment and think, what if this number said, I don't know, say 900 in our base system? What would be the number before 900? 899. So what would happen to those zeros at the end? They change to 9s, because the 9 is the largest digit we have, right? That's what happens, right? We take the number, if we have the number 900, these two digits would become the largest digit that we have in the value system we're working in, and this 9 would become N8. It would go down 1. So the same thing is going to happen with the number T00. The T is going to become what? A 9, because the number before T is 9 in base 12. And the zeros will become what? E's, because E is the largest value in base 12. Okay. Are you seeing where the 9EE came from? Because if you're not, please ask. Okay.
Use where the 20 came from on 25.
This one? Okay, so can somebody tell Nicole why in the world we have this 2 and this 0 here? Where did that come from? What if we were working in our base system? What would come after 1, 4 in our base system? 1, 5, right? The number after 14 is the number 15. Why is 1, 5 not going to work on this one? Yeah, we ran out of digits. There is no 5 in base 5. So 1, 4 is as large as we can go in that 1's place. The 4 is as big as it can go. So it's kind of like when we get to the number 19 in our base system. When we run out of digits of 19, the 9 becomes a 0, and the number before it, the 1, has to increase. So that's what happened here. Is everybody good with that idea? Okay. All right, so I'm going to talk next about how we change numbers between the number base systems. So the first one we're going to look at is taking a base whatever number, there's a blank there on purpose because this works no matter what the base is, and turning it into base 10. Okay? So we're taking something from base 2 or base 12 or base 6 or base 5, and we're turning it into our number system. So we're going to imagine that we have the number 1011 base 2, and we're going to turn it into figuring out how many we have of something. So let me do an example of something just for a moment to talk about a visual picture of what's going on when we're turning this number into something else. Let's imagine for a moment that we have the number 3, 4, 2, base 8. picture in your mind is that you have some Ziplocs. Each Ziploc has as many as we are able to have in that base system. So these are single crayons. There are 2 single crayons laying on the floor. Okay? 2 single crayons because it's the number 2. It's single because it's in the first unit's place 1. Over here, this is the bags that contain 8 crayons. I have 4 bags that contain 8 crayons. Can you imagine the Ziploc? You can even do this pretty well with boxes of crayons because there's 8 packed boxes of crayons. I think that on purpose. Actually happens, right? That's actually how you get packages of crayons. At least one of the packages of crayons have 8 in it. And then right here, this is the power of 8 that's 8 squared, which is 64. Have you ever seen a 64 box of crayons? They exist. They're lots of fun. They have a sharpener on the back and everything. So you have 3 boxes of the giant 3 packs, of the giant 64 packs of crayons too. So what you imagine is you imagine one child. Taylor, you're going to be a child. You have 2 crayons, okay? And Taylor here in the middle, you're going to be another child, and you have 4 bags of 8 crayons. And then you had the overachieving mother who sent you with 3 boxes of 64 crayons to school. And you guys are the only ones with crayons in the room. And somehow we kind of like to take a look at how many crayons we have all together, and maybe we can split them up so that everybody has the ability to draw each color, okay? So what you do is you all 3 dump your crayons out, and we want to figure out how many crayons you have. Are you with me? So obviously the fact that you had 3 boxes, and this Taylor in the middle here had the 4 bags, your 3 is worth way more than her 4, right, in terms of actual numbers of crayons. So how do we figure out what to do? Well, how can we figure out how many crayons are in your 3 boxes of crayons? What would we do? We'd multiply. We'd take the number 3, because there's 3 boxes, times the 64, because there's 64 in each box. And then Taylor in the middle, you would take your 4 bags, right? And you'd multiply that by 8, because there's 8 in each bag. And poor lonely Taylor up here in the front, I should have used a different name, but sorry. Taylor up here in the front, we know how many crayons you have. How many do you have? 2, yeah, you have 2 crayons. And in reality, it's 2 times 1 because they're singles, but you have 2 crayons. And we can add this together to figure out how many total crayons we have, right? This is the same process we're going to use no matter what base system we're in. So I'm going to go back up here now and do this with base 2 and base 12. And of course we get a value here. I don't know what the value is because I just totally made it up on the spot. But you got some kind of a value. Does somebody get it? Just for fun? No? Okay, that's fine. We're moving on. All right, so let me go back to the ones that we were actually going to do. All right, so up here at the top I have 1, 0, 1, 1. So the first thing it says I'm supposed to do is I'm supposed to put the number in expanded form. So I take each value of 1, or in the number I'm given, and I write it as a multiplication of the next value. Okay, so these numbers, 1, 0, 1, and 1 came from the digits over here. Everybody good with that? That's just like the 3, 4, and 2 down here at the bottom. And what I have to multiply by is I have to multiply the place value that they're in the base system that they're in. So since this is base 2, I'm going to use powers of 2. This one down here was base 8. That's why we use base 8 powers. That's where that 64 came from. 8 times 8 is 64. So this one over here is always the ones place. The next one is always base 2 to the power of 1. And this one will be base 2 to the power of 2. And then base 2 to the power of 3. It's always powers of whatever base you're in. Now you actually know what some of those numbers are, right? What is 2 cubed? That's 8. What is 2 squared? That's 4. What is 2 to the 1? That's 2. So you're going to multiply those numbers, 8, 4, and 2, by the number that they're beside. So this is actually 8 times 1, which is 8. This one's 4 times 0, which is 0. 2 times 1, which is 2. And then 1 times 1, which is 1. So what is 8 plus 2 plus 1? That one is actually the number 11. If you want to keep it clear in your mind, you could write base 10 next to it, that little subscript word 10. If you don't write it, it's assumed you're in base 10, so it's okay. Let's take a look at T00 base 12. I'm going to have to erase this down at the bottom so I have no space. All right, so what base am I in? I'm in base 12, which means I'm going to use powers of 12. I'm going to need 3 powers of 12, right? Because I have 3 digits. So I actually have here T times the number. We'll get there. 0 times the number. I know it's 0, but I'm going to write it out anyway so that we're clear on where everything's coming from. And another 0 times the number. So the number on the far right is always the number 1 because it's actually whatever the base is to the power of 0. And then I'm going to use the other base, the other 2 parentheses sets with the base to a power of 1 and the base to a power of 2. So far so good? Should be something up here that's still a little disturbing. The T. What's T worth? 10. So this is really the number 10. What is 12 squared? 144, you bet. And then this is actually going to be 0, and this is going to be 0, right? So what's 10 times 144? 1,440 or 14, right? So here's something I want you to write down on this. When you are moving from base question mark into base 10, you multiply. Always, always are multiplying. You're multiplying. Whatever it is times the power of base, whatever you're in. It's a multiplication process. So when you move into base 10, you're multiplying. What's this slide going to do? It's going to divide. Yes, we're going to go the opposite direction. Now we are moving from our base 10 number system into something else. So imagine, if you will, those crayons that we threw on the floor, right? We had your 64 times 3, we had your 4 times 8, and we had your 2, and now they're all on the ground. And somehow we want to put them back in the little plastic baggies so that everybody gets some crayons. All right? So we had 1,000-something crayons on the ground, whatever we had. And we want to divvy them back up in a way that makes sense into different bags. That's what we're doing when we're moving base 10 into something else, is we're dividing them up into quantities based on another base value instead of base 10. So, as you're taking a look at this, first you consider the expanded form for the base. That is, you look at what are the powers of the base you're working in. What are these powers? And then you use what I'm going to call the Divisions Scaffold. Okay, your book teaches this, and I think it's fantastic. It is a great visual imagery of what's going on. So the first thing we do, again, is it says we're supposed to consider the expanded form for the base. So this is base 4, right? So the first number in base 4 is the number 1. It's a power of 0. And then I have the number 4, because it's 4 to the 1, and that's 4. Okay? And then I have 4 squared, and then 4 cubed, 4 to the 4th, 4 to the 5th. I could do this process indefinitely, right? I can keep going. So part of the question should be, as you're looking at this, well, when do I know to stop? Well, you'll know to stop because we're going to actually want to know what these numbers are. I know the first one's 1 and the second one's 4. What's 4 squared? 16. What's 4 cubed? 64. What's 4 to the 4th? 256. What's 4 to the 5th? Guys have a calculator for that one? 4 to the 5th. 1,024. Okay, I'm not going to put a comma there because now it's going to look like it's another number. So 1024. 4 to the, we just multiply by 4 to get the next one, right? Everybody's following that? Just multiplying by 4. This is actually a geometric sequence. Did that come back up? Oh my goodness, had no idea. No. All right, so what comes after 1024? Can you do it for us? Carly, do that times 4?
4,096.
4,096. What's after 4,096? Okay, 16,000, what was it?
384.
And I will contend that that's too big. Why is 16,000 too big? It's bigger than the number we start with. So we know we can stop this process of doing powers once we've gotten a number that's bigger than the number we're working with. So the numbers that I actually need are the first ones before I got to that 16,000 because they were all smaller than the 11,000 I was given. Is everybody good with where we stop and how we go to stop? Okay. I want to show you this cool division scaffolding. If you've taken contemporary math with me, you've seen this before. If you haven't, you may not have, because I didn't used to teach this way until I saw it done in this book, and I think it's awesome. All right, so here's what you do. You take the number that you're wanting to change, 11, 0, 2, 8, and you write a sort of an extended division line like this around it. Okay? The number that goes on the left-hand side is the largest value in your power expansion, 4096 in our case. And then you take your calculator, and I want you to divide 11,028 divided by 4,096. What I want to know is how many whole number times will it go in? What's the whole number before the decimals? It will have decimals usually, but what's the whole number first? 2. Okay? What you just found out is this will go in twice, fully. Take that number 2 and multiply it by the 4096, right? Normally the 2 would be on top here if you were doing normal division. It's just going to go over here. What is the 2 times the 4096? 8192. Awesome. And then you subtract just like you would in division. So what is 1128 minus 8192? $2,000 something, right? 2,000 what? 836. Okay, so we're going to work our way down, and we're going to hit every single power. Even if it's too big for what we're still working with, we need to use every single power in the division scaffolding. So the next one I'm going to do is 1024. It's not too big, right? 1024 does go into 2836. How many times? 2. And what is 2 times 1024? 2048, right? All right, let's subtract. It's 2836 minus 2048. $700 what? 88? Okay. So 256 is next. 256. How many times does 256 go into 788? I think we finally have something that's not 2. 3. What is 3 times 256? 768. And we'll use our next power, which is actually, oh, I'm sorry, I didn't subtract yet. What is the subtraction here? 20. We'll use our next power, which seems like it's not going to yield us very useful information, but we need it, I promise. 64. How many times does 64 go into 20? 0. We need the 0 here. It's part of the solution, so make sure the 0 shows up. Well, 0 times 64 is 0, which means I've still got the same 20 left on the next step. But then I use the next power of 4, which is a 16. How many times will 16 go into 20? 1. 1 times 16 is 16, which I would subtract to give me 4. The next power is actually a 4. How many times will 4 go into 4? Once. 1 times 4 is 4, and 4 minus 4 is 0. We are not done until we divide by the number 1. Okay, so the remainder being 0 does not indicate you're done. You're done when you've divided by every single power 4 down the line. The number 1 goes into the number 0. 0 times 1 is 0, and then we're done. Your answer is right here. Your answer is 2230110 base 4. And that's why I like the division scaffolding. Your answer's right there when you're done. That's so nice. Now, a couple of things as you're taking a look. There are things that if you mess up, you should know I messed up. If you got a number on this that was a number 6, should you have messed up? Would you have messed up? How do you know? Because this is base 4. So all the numbers I'm getting out of these division step here on the right-hand side have to be numbers that are base 4 numbers. So 0, 1, 2, 3. That's it. Those are the only options, right? 0, 1, 2, or 3. So if you get a number bigger than 3, you've made a mistake. You've probably forgotten one of your powers to divide by. Okay, does this make sense to everybody? Okay. We have one more to do. We don't have time to finish it, but we are going to start it briefly. We're going to start it briefly by listing the powers that we need, and then we'll finish it next time. This is converting into base 9. So we need powers of 9. So the first one's always 1, and the second one is always the power that we're working in, 9. 9 to the 1. The next one's 9 squared, which is 81. You guys know that from your multiplication tables. What's after 81? 729? Okay. What's after 729?
7, 5, or 16.
And we're getting from 1 to the next by multiplying by 9, right, Carly? Perfect. What's next?
59,049.
Now, you probably recognize, but just in case you didn't, that's big enough. Why? It's not yet bigger, but the next one will be. I mean, this one's actually really close to the number we're trying to look at, right? The number we're looking at is 99,000. This is 59,000. It's going to go in one time, very clearly. So if you don't recognize it and you go on to the next step, you're definitely going to get a number that's too big. You can stop here once you recognize that it is large enough as well. So this is the number we would start our division with. We'll write it down, and then we'll do it next time. This is 59,049. And we'll be dividing our number 99,999 into that. That will be our first step. So we will pick up there next time.